Okay, good morning, everyone. Everyone here in person and also everyone who is listening to us on Zoom. So welcome to today's seminar series, the first of our fall seminar series. It's a great pleasure to have Professor Takao Someya here with us today. Professor Someya is the Dean of School of Engineering at University of Tokyo since 2020, prior to which he started as a faculty member since 1997 and as a professor since 2009. Prior to University of Tokyo, Professor Someya also conducted research at Columbia University's Nano Center and at Bell Labs. He served on the board of directors of the Materials Research Society from 2009 to 2011, and he's also chief scientist at RIKEN and team leader at its Center for Emergent Matter since 2015. His expertise is in the area of stretchable and organic electronics, developing the world's first stretchable electronic skin for robotic application. He was awarded the 16th Leo Esaki Prize in 2019. It's a great pleasure for us to have Professor Someya here with us today to be able to learn more about his wonderful research. Prior to me passing it over to Professor Someya, I just want to remind everyone that you can ask your questions at the end of the seminar, either by raising your hand here in person or through Zoom to directly ask your questions, or you can also type your questions through the Q&A option and I can read it out loud. So with that, Professor Someya, thank you very much for being here today, and I'm going to hand it over to you.
Good morning, everyone. So I'd like first to thank the Dr. Niroi for your kind introduction and inviting me to the special seminar opportunity. So today I'm going to talk about the electronic skins for robotics and wearables. So this is the outline of my presentation. So after a brief introduction, so I'm going to talk about the three different topics. The first topic is stretchable electronics with an emphasis for the smart apparel application. And then going to talk about the ultrathin organic electronics. And then going to briefly touch the breathable nanomesh electronics that can be directly attached on the skin for long period of time. So let me begin with showing the photo of robotic e-skin. So you may not be familiar with the robotic skin. What is robotic skin? So that is truly stretchable animal-like sensors that can detect the temperature and pressure distribution simultaneously. So now state-of-the-art robot may acquire the artificial visions and artificial ears whose performance is somehow better than human sensors. But there is no practical sensors that can detect the five of senses beyond the artificial ears and artificial eyes. So that may include the skin sensitivity. So this is the chip photo of first generation of e-skin that we made in 2004. So here you can see the 16 by 16 access transistor matrix, column selectors, low decoders are manufactured on plastic foils and then assembled together to complete the readout circuitry. And then we can complete the integration between the pressure sensors and the readout circuitry simply by using the lamination approach. So do you know how many pain points are there on your surface of skin? That's actually 2 million or even more. So currently, the state-of-the-art robot may acquire the tactile sensors on the fingertip, and then we need to put the individual cables. But it is almost impossible to put the 2 million of cables onto the individual sensors. So how we can solve this problem? So we learned the development history of liquid crystal display that may begin with the 7 segment used for the calculator, going to the passive metrics and active metrics, where few transistors are integrated for individual cell. So by utilizing the active metrics layout, the number of cables can be reduced from 1 million to 1,000 plus 1,000 at the edge. And if I use the low decoders and the column selectors, so we can further reduce the number of cables down to 10 plus 10 plus something. So in that way, we can establish the scalable circuit design to get the signal from so many sensors on curved surface. We are dreaming this situation, and robot with sensitive skin may feel and even respond to a person's warmth while shaking hands. They consequently letting people feel that robots are warmer. So our robot skin concept was featured by Time magazine as one of the best invention of the year. So since then, we are working very hard to establish the high throughput manufacturing process line to make the active metrics for large area sensors simply by using printing machine. So here you can see the robot arms moving the plastic foil, which are supported by the glass substrate. So we can manufacture the high definition active metrics by using only printing that includes the gravure offset, inkjet, screens, and others. So this movie shows you how our device works. So it doesn't look like flexible devices, but those active metrics used to be manufactured on glass substrate, which were, of course, very fragile. Because our devices are manufactured on plastic foils, and this kind of jumping motion doesn't cause any mechanical failure. So in that way, we can achieve the high spatial resolution and high data speed readout simultaneously. And our device can detect the temperature distribution and pressure distribution simultaneously. And also that can wrap around the cylindrical bar, and we can monitor the grip pressure in this 3-dimensional configuration. So immediately after fabricating the bendable electronic skin, we instantly recognize that how important to introduce the stretchability to the robotic skin application. So without stretchability, we cannot apply e-skins onto joint of arms like a movable part. And also it is impossible to apply e-skins onto 3-dimensionally curved surface like robot body. So how we can make the stretchable integrated circuit? Our approach is quite straightforward. So first, we put the 2-dimensional array of rigid island, which are embedded in rubber substrate. And then we can make the organic transistors by printing. And finally, source drain gate are connected by utilizing the printable elastic conductors. So in that way, when we stretch our devices, all the strains are accommodated with changing the length of wires. So in that way, we can achieve the stretchability over 145% without causing any mechanical defect. So to build the stretchable integrated circuit, the newly developed elastic conductors play a very important role. So we can print the elastic conductors once onto the rubber substrate and anneal at 140 degrees Celsius. And then we can achieve the high conductivity close to the 1000 Siemens per centimeter and stretchability over 400% simultaneously. So you may see the bright light emission from LED, and brightness doesn't change at all. So this means that the change of resistivity is sufficiently low. So this is quite a unique feature for our elastic conductors. So ink formulation is quite straightforward and easy. So we add the silver flake among the fluorinated copolymer with adding the organic solvent and surfactant and mixing everything together and print once on the elastic substrate and anneal at 140 degrees Celsius. When we observe the cross-section of elastic conductor, we eventually realize the silver nanoparticles are naturally formed and densely and uniformly dispersed among the rubber matrix. So this is the magic of nanotechnology. And in that way, we can achieve the efficient percolation conduction through silver nanoparticles that are naturally formed from a silver flake in the dimension of 2 to 3 micron. So this is the one of the example how our device works, and we can put the elastic conductors on the soft gripper used for the robot arms. And here we can put the 8x8 flexible pressure sensors. And then we apply the same force to the soft ball, and then contact that the area is fairly large. And this ball is hard, and it looks similar, but when we apply the same force, the contacted area is much smaller. So in that way, we can distinguish the material stiffness by using the flexible temperature pressure sensors. And our elastic conductor can be printed on rubber substrate, and then the rubber substrate can be transferred to the textile substrate with applying the heat and pressure, a so-called hot melt technique. So in that way, we succeeded in the electrically functionalizing the surface of textile substrate. So now that approach is creating the new industrial opportunities in the field of smart apparel. So the left figure shows the state-of-the-art electromyogram monitoring system that are still widely used in sports field. So here is the gel electrode that's connected to the external cables and read out module containing battery and wireless tape. So this is state of the art, yet this arrangement may not be so convenient for monitoring athlete motion because the external cable is always troublesome and easily detached during the harsh motion of athlete. But now all the electronic elements are embedded in the surface of sportswear containing the electrode, cables, and readout circuit. So the commercial product can monitor the ECG, EMG, body temperature, and motion, and creating the new application opportunities in the sports field, or monitoring the posture balance, and to evaluate the recovery of rehabilitation. So next slide show you the smart wears that can monitor the user's motion. So this smart wears contains the 7 accelerometer. And by utilizing the AI analysis, we obtained the user's motion very precisely in real time. So those kind of motion capturing system usually requires the multiple camera setting and then put the markers on the clothes. However, our Smartwear doesn't require any multiple camera setting, and we can precisely monitor the user's motion anywhere, anytime. So even the outside during the marathon or playing golf. And it is so easy to monitor. So just wear our smart clothes, and calibration required 2 seconds. And then immediately after the initial calibration, that can start the user's motion very precisely. So one of the tangible goal will be sports application. So she's Miss Umehara, member of Japan's national team of taekwondo. So during the corona situation, the Miss Umehara found difficulties to meet her coach in person. And then she obtained our Smartwears. I'm sorry that some characters written in Japanese, but you may see how our device works. And she obtained our device during the corona situation, and her motion was transferred to her coach remotely, and she obtained the feedback from her coach by online. So those kind of system has been utilized actually during the corona situation. And another example is rehabilitation or remote rehabilitation. Person with spinal cord injury participated in a rehabilitation session at home with prototype and communicated with his therapist remotely.
Stretchable electronics.
And this is another application of smart glove.
With DNP's new wiring and mounting technologies, stretchable electronics can offer a pleasant wearable experience. Unlike conventional glove-type devices, stretchable electronics can be attached flawlessly onto the wearable component. Here are some features of stretchable electronics. They are highly stretchable and have low resistivity. The resistance is stable while extended. Our devices are robust after stretching 1 million times. Any electronic component can be mounted onto the stretchable electronics. This is a smart glove with an inertial measurement unit attached using our technology. Our device can capture finger motion accurately with superior fit. Let's realize the metaverse together.
So in that way, we integrated the multiple accelerometer in glove-like tiny space. And another example is Smartwear to monitor 3D ECG. So this is quite exciting latest progress. And to monitor the ECG, the patient have to go to the hospital and then put the discrete gel electrode, and that's connected to the external module. And then the patient have to go back to the hospital, return this element. So this is quite inconvenient. But now, what we developed was Smartwear, where the all the electrodes are embedded in appropriate position of the body. So in that way, we succeeded in developing the world first made inspection of 3D ECG. So this device obtained the medical device class 2 certification, and also insurance coverage has been approved in Japan this March. So we always say the Smartwear is so easy to put, but we didn't really recognize what does this mean exactly. But this is one of the good example how the Smartwear can utilize indeed when we need to put the sensors at the appropriate position of the body. People usually have to go to the hospital, but now all the elements can be embedded onto the surface of body. So this is the example of how the Smartwear can be used. And then I'm going to talk about the conformal sensors. So this is very famous development reported by Professor John Rogers. So Professor Rogers reduced the silicon tip down to a few micron. That's temporarily supported by the plastic foil and then laminated on the surface of body directly. So they called this technique the temporal electronic tattoo or epidermal electronics. The Professor Rogers reduced the thickness of substrate starting from 500 micron, 100 micron, 36 micron, and 5 micron. So in that way, the reduction of this substrate thickness can establish the good physical contact on this human skin. And in that way, they achieve the significant improvement of signal to noise ratio, monitoring the electrophysiological signal like ECG or EMG. So this research triggered the extensive effort of researchers to introduce the electronic function on the surface of body or skin. So now there are many reports related to the skin electronics. And on-skin sensors may detect the ECG, EMG, EEG, hydration, body temperature, skin modulus, and sweat analysis, including lactic acid and glucose. So next I want to show you the world's thinnest and lightest organic thin film transistors that was published in Nature magazine in 2013. So it's floating in the air and lighter than feather. But of course, you may know the falling velocity doesn't depend on the mass of object. So this movie doesn't show you any evidence of lightweight, but when our devices was reached to the ground, it doesn't cause any mechanical failure. Our substrate thickness is as thin as 1 micron, that is factor of 10 thinner than kitchen rug. And thanks to a thin film feature, that may achieve the amazing conformability and apply to the complicated surface, and crumpling doesn't cause any mechanical failure. And we used commercially available PET or PN film with a thickness of 1 micron. After fabrication, we prepare the pre-stretching rubber and laminated our devices onto the rubber with utilizing the wrinkling structure. So the last step is quite important, and then I want to show you the fabrication process in detail. So here is the 1 micron thick substrate having the organic devices on the surface. And here is the pre-stretching rubber and laminated together. And after the relaxation of pre-stretching, the rubber starts shrinking, yet the ultra-thin film doesn't shrink at all. So in that way, we can make the accordion-like wrinkling structure. So this is the cross-sectional SEM image. So here is the wavy structure. And if we look at the bending radius very carefully, it changed from 15, 20, 18, 10 micron. However, the minimum bending radius of our devices was as small as 5 micron. The devices manufactured at such a sharp bend area doesn't cause any mechanical failure. So this movie shows you how our device works. And this is the original position and start shrinking. So using the accordion-like structure, we succeeded in transforming ultra-thin film devices to be stretchable. Another example is the world first stretchable organic light emitting diode. And so here is the original length and start shrinking. So we are doing the almost identical thing. So we manufacture the high performance semiconductor devices on ultra-thin film, and then delaminated from the supporting substrate, and then laminated on the pre-stretching rubber. So in that way, we can make the stretchable devices so easily. And then we start integrating the multiple electronic functions on ultra-thin film. So one of the good example is ultra-thin pulse oximeter, where red pellet, green pellet are integrated with organic photodetectors. So we didn't invent any new sensing mechanism, but we try to keep everything to be thin. And then when our devices are put onto the fingertip, the sensor attachment doesn't cause any discomfort of wearing, and we can achieve the good physical contact on the fingertip. And then slight motion doesn't cause any degradation of signal quality. So this is the just single point detection, but now we succeeded in developing the two-dimensional array of photodetector with integrating the organic photodetector and low temperature polysilicon active matrix. So we achieved the high spatial resolution over 500 dpi and high read out speed over 40 frames per second. So this is the circuit diagram and a cross section of the device structure. So we first fabricated low temperature polysilicon thin film transistor active matrix that's originally developed for the readout circuitry for liquid crystal display. And then we deposit the organic photodetector on the surface of low temperature polysilicon. And this is the module of wearable type imaging sensors. So here is the flexible imager, and we put the near infrared light emitting diodes that rely on the rigid tiny element. And to avoid utilizing the conventional optical lens, so we put the flexible louver to achieve the high spatial resolution inside the body. Now, when our module are put on the fingertip, we can monitor fingerprint or position of veins that are utilized for the biometric information. Simultaneously, we can monitor the pulse waves like vital signs. So in that way, we can monitor the vital signs and the biometric signal simultaneously by using the same conformal imaging system. And finally, I want to explain the breathable nanomesh electrodes. it firmly adheres to the shape of the skin, and it is ultra thin and lightweight. There is no sense of fit. So let me show you one video that takes 1 minute.
I'm Takao Someya, a professor at the University of Tokyo. Our on-skin sensor utilizing nanomesh electrode is ultra-thin, lightweight, stretchable, and breathable. It is capable of monitoring health conditions simply by pasting it onto the skin. New sensor can be worn on the skin continuously for a week without causing any inflammatory issues. Our skin display is a 24 by 16 array of micro LEDs, and it exhibits simple graphic with motion. Because it is made from thin and soft materials, it can be freely deformed. The skin display also showed an electrocardiogram measured by using nanomesh electrodes. Combined with a wireless communication module, the acquired biometric data can be transferred to a medical cloud, and your home doctor can monitor your health conditions while you stay at home. In the future, we envision human-friendly skin electronics that will lead to improving the quality of human life.
So I hope that you like this video, and let me try to explain the detail of nanomesh. So nanomesh is made of polyvinyl alcohol by using the electron spinning method, and the gold patterns are formed by vacuum evaporation through a shadow mask. And when nanomesh is placed on the surface of skin with applying the water by spraying, the PVA is dissolved water and washed away completely. Finally, only gold thin film nanomesh remains on the surface of skin. So this is the nanomesh electrode put on the fingertip, and the shining part are gold. So that looks like a continuous gold film. But if we magnify the gold layer by SEM, it's porous structure. And this is the magnified image. So this is the gold region and the non-covered region. And the dark spots are sweat pores. So if we look at the sweat pore region carefully, the same amount of sweats are penetrating from the sweat pores. So such kind of breathability or natural penetration of sweat or vaporization of sweat are very important to ensure the biocompatibility. So indeed, when nanomesh conductors are attached to the people's forearm continuously for a week, so none of the patient doesn't show any doubtful inflammatory issues, while the 1 millimeter silicone and 1 micron thick polyethylene, both of them are known as a non-toxic and biocompatible material, yet that exhibits the fairly large risk of inflammation. So in that way, we eventually realized the breathability is quite important to enhance the biocompatibility. And then nanomesh is placed near patient chest, and this could be connected to the external module embedded into the Smartwear band. And in that way, we succeeded in monitoring electrocardiogram waveforms in real time, and the data was transmitted to the smartphone wirelessly. The previous experiment was just the electrode. And then we are going to manufacture more advanced electronic function. So one of the example is all fiber-based mechano-acoustic sensor. So here we utilize the 3 nanomesh layers. So top electrode and bottom electrode. The intermediate PVDF layer is sandwiched between 2 nanomesh electrode. And then that can monitor the heart sounds precisely. And that can be attached near people's chest. And then heart signal has been successfully monitored continuously for 10 hours with high signal to noise ratio of 40 dB. And we didn't see any severe degradation of signal quality after continuous monitoring for 10 hours. Another example is on-skin pressure sensors. So we are able to measure the contact pressure without affecting the skin sensation when fingertip touch an object. So our skin sensors are manufactured by laminating the 4 nanomesh layers. Here is the bottom nanomesh electrode and nanomesh insulator, top electrode, and the surface is covered by protection layer. So in this way, we have made the capacitance structure, and when we apply the pressure, the spacing between 2 electrodes get closer, which increase the capacitance. So one of the highlights of this research is how we can scientifically prove the nanomesh attachment doesn't make any influence on skin sensation. How we can do that? So here is a way to show the no effect on the skin sensation by sensor attachment. So we lift up some object and monitor the minimum grip pressure to lift up this object with covering the fingertip by some materials. Indeed, when the fingertip is covered by very thin plastic foil like 2 micron, the minimum grip pressure is slightly larger than the bare skin because skin sensation is affected by the film attachment. However, we realize the nanomesh attachment doesn't affect the any skin sensation, and then the bare skin and the nanomesh looks identical with monitoring the grip force. And then we prepare the very soft sponge with a weight of 0.16 gram and try to lift up and to monitor the grip force of sponge. So in this way, we succeeded in measuring the contact pressure when lifted the sponge ball with a finger. And then this slide shows you the pathway to the skin electronics. As I mentioned, our research was originally motivated by the development of robotic skin and achieved the bendable merge point, merge modal. And robotic skin application required the stretchability, and then we manufacture the world first stretchable integrated circuit. And then our e-skin can be applied onto the 3-dimensionally curved surface or movable part. And reduction of thickness can improve the conformability. And then at that time, I expand our target object from robot body to the human body and start monitoring the biological signal. But continuous and direct attachment of sensors on skin required the biocompatibility. And then we achieved the breathable nanomesh that allowed us to monitor the biosignal for longer period of time without causing any inflammatory issues. So before concluding my talk, I would like to acknowledge my collaborator. And here is my group photo, and Dr. Tomoyuki Yokota and Sunfun Lee and other members has made the nanomesh electrode or ultrathin electronics. And clinical evaluation was performed in collaboration with the Keio University Hospital, led by Professor Amagai. So in summary and conclusion, today I talk about the recent progress of next generation of wearable electronics, and ultrathin and soft material can be utilized to harmonize with human. And I hope that such a stretchable and soft electronics can realize the novel application in the field of healthcare, biomedical, welfare, sports, and even more. So thank you very much for your kind attention.
Thank you. Thank you, Professor Someya, for a wonderful talk. We have time for a few questions. You can, again, raise your hand and directly ask your questions, or you can type it through the Q&A. So we have a question here in person.
Dr. Someya, thank you so much for such a wonderful presentation. This is very impressive work. Can you speak a little bit to the power and data transfer rates with these different thin films? Is power inductively applied, or is there any kind of power capacity? Is that a challenge that's being worked on now? Thank you.
Okay, thank you very much for an important question. So our nanomesh electrode, of course, requires the power supply and the data readout module. And that rely on the all silicon-based conventional microelectronics. That means the most critical issue is how we can establish the reliable interconnection between nanomesh and such module. And currently, we are using just metal-metal physical connection that works fairly good. But ideally, we want to supply the electricity wirelessly without any physical contact to improve the reliability and mechanical durability. So that will be addressed to the important future research direction. And answering to your question, so we utilize the all conventional silicon electronics. So that is usually limited by the just standard device performance like Wi-Fi or ultra low power Bluetooth.
Thank you. So we have several questions online. I'm going to read out a few of them. So no matter how good is stretchable thin electronics, you still would need a battery. Can the battery also be made thin and stretchable?
So that's also quite interesting and fundamental question. So the big question is if all the elements have to be stretchable or not. So as far as the sensing element that need the intimate and conformal contact on skin definitely requires stretchability. However, if the power source is placed somewhere like smart watch or others, and supplied the electricity from smartwatch to the nanomesh electrode, it is reasonable system design and to utilize the conventional rigid battery. But of course, it is good to have a stretchable battery or other electronic functions to make the fully stretchable electronics. But that might be too difficult at this stage. And to make the more practical, system design today. So I like to combine the, or I like to utilize the existing module to make the reasonable design of a system very quickly right now. That might be the answer to that question.
Yeah. So regarding elastic conductor, so can this replace E-chain or other expensive insulating material when using this on a robot or robot arm?
So sorry, could you repeat your question?
So regarding the elastic conductor,
Yes.
Can this replace? Right now we use E-chain for or moving the robot arms, and we use mostly for the moving parts. And now we use some of the expensive insulating material to avoid damage inside conductor or the cable. So can this replace those expensive materials there? That was my question.
Okay. So because I'm interested in large area electronics, the cost reduction is one of the major challenge for the industrial application. And that may also include the nanomesh or others where the gold is used. So to reduce the material cost, replacing the gold with other cheap metal or carbon may be very important. And that's also beneficial to improve the biocompatibility. And as far as the elastic conductor is utilized, so here we are using the silver flake. The silver is not so expensive in comparison with the gold, but yet that is expensive. So we should work hard to replacing with silver with other cheap materials to reduce the material cost in the future. So thank you very much for your question.
Thank you.
Thank you. So there is a question online asking about the biocompatibility of your nanomesh electrodes. So the question is, are they poisonous at all? And also, how stable can they be, both mechanically and chemically?
Okay, so that is also quite important question. So in the end, our nanomesh electrode is just simply thin film gold, because PVA is utilized as a sacrifice layer and washed away completely. And such a thin film gold is not robust enough for long-term use. So to improve the mechanical durability, so recent device model utilize the polyurethane and the combination of polyurethane and PVA. And in that way, we add some strengthening material to improve the durability of nanomesh. However, what we are thinking is just 1 day lifetime. Indeed, when the nanomesh is utilized for monitoring ECG or other biosignal, and then taking shower, remove the our nanomesh completely, and then we put the fresh nanomesh device after taking shower. So in that way, what our target lifetime is just 1 day. So we have already proved that some nanomesh device can continuously monitor ECG for 1 week. So in that sense, our device can have have already met our requirement. So what is the remaining issue is the reduction in cost, because the disposable devices have to be cheap. So that's one of the important remaining issue. And another remaining issue is we can compromise we can also improve the usability. So that is also quite important for medical application.
Great. So there's also a question asking if you can comment on industrial applications beyond medical usage.
Okay, so that's also important question, and I want to know the answer from the expert or other industry people. And so might be entertainment, sports, gaming, or even fashion. And medical application is quite important, obviously, and the performance required for the specification and requirement for the devices can be specified by the target medical application. And that is quite important for engineers. But for fashion, may require the good design, and that is not the good homework for the engineers. But I believe there are tremendous opportunities for smart wares in industry beyond the medical application in the future.
Great. So last two questions. Can you also design your devices to actuate and stimulate your body? For example, move your fingers remotely in addition to sensing.
That's also quite fascinating and important question. So currently we are focusing on the sensing up functions. However, the actuation and stimulation, or maybe drug delivery or combination of a microfluid channel will be the most important direction in the future. And currently, we started working on the electrical stimulation, but the more advanced actuation may be integrated with this kind of on-skin sensors to create the new application opportunities in the future, as I believe.
Wonderful. So last question. So you talked about trying to bring the cost down. So related to that, is it possible to recover and recycle your gold nanomeshes?
Sure, that is also quite important question. So I'm not 100% sure if the gold is allowed to use for the most industry application. So if that is true, so recycling will be quite important task for us. But we are currently trying to replace the metal with carbon-related material from the viewpoint of cost reduction, and the recycling is not so easy. So because how we can collect such material after the taking shower. So, but that is quite an interesting question, and we should carefully think about the possibility of recycling in the future.
Great. Thank you, Professor Someya, for a wonderful talk again, and for your time, even though it's very late there for you. If there's no other questions, we thank you again, and thank you all for attending.